Welcome to Unit 4. We're on Unit 4. We're on the fuel cooler bracket. We're in geometric tolerancing applications, and I have a nice problem here for you. It should be a straightforward, simple problem. And let's take a look at our problem. Now, this is a fuel cooler bracket. This here is an example, an application of a large truck. This is a large 18-wheeler truck. And this here is its frame rail. So you can imagine I have a frame rail on this side and I have a frame rail on the other side. Now, this being a diesel engine, they have a fuel cooler. This is this green fuel cooler. You see it has some lines going up to the engine to cool the fuel. So this is the arrangement that they selected here. We have these two brackets. There's a blue bracket here and there's a blue bracket here, and it's attached to the frame rail, and it's bolted on with two bolts. And the size of those bolts, those are M16 bolts, and then I also tell you what size the holes are in the frame rail. And the size of the holes in the frame rail are 17.5 plus 4 minus nothing. And then where it mounts to the fuel cooler itself, we have four M8 bolts. And what we're interested in doing is tolerancing this blue part over here and be able to select our datums and be able to tolerance it so the part goes together. So understanding a little bit how the part works, let me show you a little bit better here. This here is all the data that you will need, the fuel cooler, and it looks like it's enough information for you to be able to tolerance the part. So, and remember, what you want to do is read the discussion in the beginning of this unit. That'll tell you a little bit more about this assembly. So this here is a 3D example. And it was very similar to the grommet, where I would like you to try and tolerance this thing in 3D rather than tolerancing in 2D. Just give it a try and see how you like it. All of the dimensions will be in the CAD file, so you don't have any dimensions. You'll see the CAD file for the dimensions. The only thing we're going to have is we're going to have the size of these holes and the size of these holes. All the dimensions will be basic. And so we're looking for you to apply the tolerancing. And this would be similar to the way that I did it on the grommet that we did earlier. Now, if you really don't want a tolerance in 3D, that's all right. There's an example in this book. You take a look in this book and you'll find an example where it's a 2D example also that has all the dimensions. If you want to apply the tolerancing, you can have your choice. Do it either way. Now, normally what I have done in the past, I have you select the datums and I come back and finish it. This one here, I'd like you to think about it. Remember, mating surfaces are what we're going to call datums. Remember how that works? You're going to pick the leaders and then you're going to tell the followers to follow along. So this being a simple one, what I would like you to do is just take this one and tolerance it all up yourself the best you can. I want it fully defined. And when you're going to put geometric tolerancing on here, I want to have tolerances and I want to know where they come from. What was your reasoning, why you put the tolerance, where it came from. Anything that you think is necessary to make this thing a good functional fit. So if you're in work groups, there might be, you can work with somebody else there and tolerance this part. So I'm going to give you a few minutes to tolerance it. And then we're going to come back and I'll show you how I approach the problem. So we'll see you in a few minutes. Okay, welcome back. We're on a fuel cooler bracket. We're going to take a look at the solution, what you did, and then you can compare your thoughts with mine. And you might like what I did, or you might like what you have already. This here is just offering you some suggestions. Remember, the Y14.5 standard doesn't tell you how to do it. It just provides you the tools. Doesn't tell you how to apply tolerancing. It just gives you the tools, and then you use the tools any way you want. So this here is some suggestions, some guidelines from my experience. I travel around to a lot of different places. I see a lot of different things, how I would do it. Now, I'm a little slow today. I had kind of a rough night last night. I got in very late and later than I expected. The flight was late as usual, and I got into my hotel room real late. Got up this morning, had trouble getting out of the room. I tried to get out. There was only two exits out of the room. One door went to the bathroom and the other one had a do not disturb sign. So it took me a little while to figure it out, but I finally got out of the room, so I'm here. So it might be a little slow today. All right, let's take a look at our problem here. You notice the way the part mounted. It mounted up against that face. So what I did, I picked that as the primary datum. Now, why I picked it, let's take a look at the model. See, here's my blue bracket. And we'll imagine that this is the frame rail on a truck. When it mounts up to the frame rail, this is the way I saw it. It mounts up against that frame rail, and it mounts tight up against her. I'm going to take some bolts, and I'm going to tighten those bolts, and it is going to the frame rail. It is going to go up against that frame rail, and it's going to be tight. And what I saw is this was the follower. That will be wherever this puts it. Now, sometimes, because remember what I told you is that we want to be able to look at how the part mounts, the leaders and the followers. Now, some people say, well, you talked about datums where it mounts. It also mounts on this surface, and it does. It does mount on that surface. But if I was to call this the datum, you see, and I said that was the leader, then you see what I'd have to do is, since that's the datum, this surface is going to have to come in and have some tolerance to tell me how much it can be off. Well, if I said that this could be off within 1 millimeter or 2 millimeters, you see, it's not going to be off. When it goes on, it goes on. And what happens? This surface is the one that's off. So the way that I thought of looking at it is that I said, okay, what's the leader is, this is the datum, it mounts up against that face, and this is the one that's going to be off. So if I'm imagining I'm standing on a truck, it's mounted up, and I point to that surface, and I say that surface can move within 4 millimeters, that's how much the fuel cooler is moving around on that surface. Now, probably, of course, if you're the fuel cooler designer, you know that you probably think that this is the fuel cooler, that's 0, and then the frame moves to your fuel cooler, but that's probably not the way that it works. So that's why I selected the face was the datum. Now, if that face was the datum, that sets the attitude, and the primary datum is one of the most important, right? That sets it up. Now, what locates this thing back and forth? What I saw is it was located by these 2 holes. These 2 holes, you notice they do everything. They stop it back and forth. They stop it up and down. They stop rotation. It's the 2 holes. Now, I didn't pick one hole as datum B and the other one as datum C. I really didn't do it that way because that's not the way it works. I can't say, well, okay, that's the datum B and the bolt is right in the center of that hole and this hole is off. The way that I would see it is you have 2 bolts goes into the holes. Both of the holes do the locating. They stop it up, they stop it back and forth. So I call both holes the datum. So let's take a look at my detailed drawing here, and I'll show you what I did. So on the drawing here, this is what I did is I said that those 2 holes were positioned, and they were positioned within a diametral zone of 1.5. Now, where I got the 1.5 down here is I did the floating fastener formula. I took the MMC of the hole, and the smallest hole that I have here is a 17.5 hole. If you're having trouble seeing this, you should have this on your detailed drawing, so you can take a look at it there. And then I took the MMC of the fastener, and you remember earlier in a unit it showed that the fastener was an M16 bolt, so I took the difference between them and I had 1.5 position. If that gave me 1.5 position, that's where I could put the 1.5 position on this hole down here. And that's the position. And I just positioned it to A, and then I called both of the holes datum B. So it's the 2 holes. The centroid of the 2 holes would stop it up and down. So that's my datums. I don't need any other datums, that's all I need. Now, once I got my datums, I have the datum features related to the datum surface frame. Now I'm going after it. I'm going to tell all the features. You follow along. So what is it that's important? I'm going to go after the important things first. So let's see, what's important to me? Well, it's that surface there. That surface is what I'm interested in. Why I'm interested where that surface is, you see, because that's where the fuel cooler mounts. It mounts on that. So if I'm holding it right here and I say that surface can be off within 3 millimeters, right, the math data you'll find in the CAD software, that tells me where that is. So that surface can be off within 3 millimeters. It can move back and forth from where it was supposed to be, where it's defined with the basic dimensions, and it can be off within a total of 3 millimeters. That's 1.5 either way. Probably could have even been a little bit more. You know how I'd figure my tolerance if you had 2 brackets, and I was on here. This bracket could move a total of 3. This one could move a total of 3. You can see if that one went out 1.5, this bracket went in 1.5. That the angle on that fuel cooler bracket, it could tilt in here, couldn't it? Can you imagine it being tilted in here? It's only tilted 3 millimeters. That's very, very small amount of tolerance. Then you're thinking of it that way. If this is real far apart, right, 3 millimeters doesn't mean much. If the brackets were closer together, well, then that would mean a lot more. So actually analyzing, you might even be able to have more tolerance. It depends what you thought was in the area. You know, if you have other hoses or you have drive shafts or exhaust systems or what's going on. I didn't show you the rest of it, but the idea here is to get it across where that tolerance comes from. So that's really what that's doing is locating that surface. The next thing I did was come in and I located these holes. And these holes here, I have the holes, let's see, they're 9 millimeter holes. And there was 4 of them. And what I did is I put a position tolerance on those holes, and I positioned them back to my datums, A and NB. And the how I figured the tolerance in there of 1 millimeter, I took the MMC of the hole, which was 9 millimeters, the MMC of the fastener, which was 8 millimeters, and then I had a 1 millimeter position. So 1 millimeter, since this was a floating fastener, I was allowed to take 1 millimeter and give it to each part, right? So the fuel cooler had 1 millimeter, this one here has 1 millimeter. Now what about the remaining features on this part? Also, do you notice what I did here? When I did this fuel cooler, do you see that? I did this as a partial datum. In other words, it only mounted on this area here, so I didn't see it was necessary to be able to control the tolerance all the way. So I would have to give you a dimension where that was, right? Because that's where, if I was going to probe with a coordinate measure machine or build a gauge to be able to come in and make sure that that fell within, I'd only want to check that area. That has to be within 3 millimeters. And what about the bend and everything else in here? Well, the angle and what arc, who really cares what that is? What the engineer is really interested in is where this surface is. This is the leader, and then where that surface is. And what is this stuff in between? All that stuff in between holds this important surface relative to that important surface. That's all we're doing here with this thing. So remember with geometric tolerancing, the difference is you point to the feature and you tell me that feature better be there within so much, and that's what we're doing. See? Symbol goes right to that surface. All right. Now what about the rest of the features on here? I thought the other features weren't very important. I kind of lost interest here. There was nothing else. So you notice what I have is down here on the bottom, I have a tolerance unless otherwise specified. Everything else is profiled within 4 to the datum reference frame A and NB. And so that means this outside edge, the periphery on this outside edge is within 4. All of this here is within 4. The outside periphery on here was in 4, right? So everything else has a general catch-all tolerance. You notice what I did is the datum reference frame that I established was A and NB at MMC. And why I said A and B at MMC is, if you take a look at my assembly here again, MMC would come up and it would put 2 virtual size pins in here, and that means that this bracket in the assembly, what I could do is I could move the thing around to be able to get this bracket to come on. See, there's really not too much. How much will this move up here? Well, you see you have the distance between those 2 holes. The distance between those 2 holes is very short, doesn't it? See that distance is very short? If I take a look at it at a ratio here, 1, 2, 3, 4 times as much. So if these holes were spread further apart, he would locate this part better. But since they're so close together, it's really not going to be able to locate this up very well. So MMC, what it allows these holes to be able to move around. I put it on the bracket, I can adjust the bracket, fixture it where I want it, and then be able to bolt it up. Let's take a look at the assembly drawing. You know, ideally what I'd like to do is take this thing and mount the bracket. Now what they tell me is that these brackets, they would like to bring them into paint. Put the brackets on. This here is your frame rail. I have the 2 brackets. Bolt the 2 brackets on and then send it through paint and paint everything. Then afterwards put the cooler on. Well, if we're going to do that, we're going to have some problems here. You can tell that right away. Remember how we talked about those holes right there? They're so close together. We had a lot of tolerance on them. And if they did, you can see these brackets. This bracket's going to hang this way. This bracket's going to hang this way. They're going to be hanging on there loose. So the only way you're going to be able to get this part to go together in an assembly, when they're mounting these brackets and they want to tighten them up tight to go through paint, they're going to have some type of fixture. And the fixture down at the assembly line, they're going to have to fixture where these 2 holes are, tighten them up, so later on this fuel cooler bracket would mount on. So if you were a designer, you would have to plan for something like that. Now if they tell you, well, we don't want any kind of a fixture, we don't want a fixture, we just want to be able to put it up and bolt it up, well, you're going to have a pretty hard time, right? I mean, you're going to almost have to dowel this into the frame. And the reason is that you see how close those holes are and how far that distance is away? It's just going to be pretty hard to hold that tolerance tight enough to be able to get anything up here. Now sometimes I've seen the way the engineer will design it is that I have a hole on one side and a slot on the other side, and I can make the hole the same size as the bolt and then a slot, and that could certainly help. But still we have a serious problem is that the distance here is so close and the distance here is so far. So this is probably going to have to be fixtured and able to put it up together. So allowing an MMC modifier just allows extra tolerance on these holes, knowing in the end that thing is going to have to be fixtured up. And how much they could move around would be the max material on these holes. You know, what we'd have to do is we'd have to figure the worst case outer boundary, and that would tell you the worst case that these things could be off. Now this here is the actual detailed drawing, and I drew this thing up. The thing is kind of small. You should have a picture of this in your workbook. And notice this one has all dimensions on it. Now sometimes people will send this thing along and show you what all the dimensions are. And what I could do is I could apply the tolerancing to this one. You know, that face there on the side would be datum A, the holes would be called off as datum B. That surface I put a profile on, and then that upper surface I put a position on. Now this is pretty small, so you'll have to take a look, but this, you take a look at that drawing and that'll show you how I toleranced the part in 2D. And then down on the bottom here, I put the tolerance on unless otherwise specified. So you can take a look at that on your detailed drawing and see what I did. This is actually tolerancing the part if you want to actually put the tolerance on the 2D part. And sometimes they'll tolerance the part, they'll just send this drawing along to give you the dimensions. And then if you want to know the tolerance, you take a look at the other drawing. Because you know that this course here, we call it a dimensioning and tolerancing course, but really this is a tolerancing course. I mean, the dimensions, where you put the dimensions and where they come and go, doesn't really have anything to do with it. It's tolerancing. We're interested in the tolerancing. This is a tolerancing course. Dimensions, that would be drafting 101. Now here's a little functional gauge that I drew up. And to give you an idea how the part would fit on this gauge, and to just check the things that we have done. You see it's a gauge that would look like this. We have that back face. We would take the bracket, we would mount it up against that face, and we mount it up against the face. These are the two pins that are going to hold it, and those would be virtual size pins. In fact, let me put up the tolerances on those pins. Here is the sizes. These would be 16 millimeter gauge pin sizes. Right? That's going to be the virtual size. You take a look at the drawing, then you compare these gauge pin sizes. And then back here is going to be a feeler gauge check. And then up here is a face. That's going to be a 3 millimeter profile check to make sure that surface falls within the zone. And in here, it must accept 8 millimeter gauge pins. See this on the outside here, that periphery, I think we had 4 millimeters. Probably that won't even be checked. Probably the first part would be checked, and then after that, we wouldn't check it after that anymore. And if you take a look at the models, I have a picture of that. I have a sample of that gauge right here. This is the gauge. Now these pins obviously would have to remove to be able to get it on. This is plastic, so I could put it on here for you, but this is only a concept gauge. You notice when I put it on, I'm bringing it up against this face here. When I bring it up against that face, I'm going to be pushing it down, holding it down on that face. This is going to be a feeler check over here, right? It must accept these two pins. These are going to be virtual size pins. If they're virtual size pins, then over here, these are virtual size pins over here also. And the gauge pin size you should see in the workbook. You know, it'll tell you what the size of the hole is, and you can see that they're 8 millimeter size pins. And then back here, this is going to be a feeler gauge check, you know, that I'm going to come in and make sure that surface. I could also have some sensors back here seeing how far that is away. And, you know, sometimes designers say, well, I'm not designing gauges. Why do I want to know where the gauge looks like? The idea here is why I show the gauge. It sometimes helps you understand the concept a little bit. It's not so much we're designing gauges. What you're looking for is you're looking at a 3D solid. So imagine it's a 3D solid. This is where the part mounts. It has to fit within these boundaries. So really we've defined some boundaries. You notice down over here, we're not even checking anything here. That's not important to us. I mean, get down to the important things, and that's what we did. We picked the face, the datum, the two holes, and then these over here. Now the MMC and the datum, you know what that's going to do is that's going to tell us down here we have virtual size pins. And if you have virtual size pins, you have 16 millimeter gauge pin size, and the holes got a little bit larger. Remember, the holes could go, I think, up to 17.5 or 4, whatever that was. When it goes on, you see what's going to happen. It's going to wiggle around on this gauge. It's going to wiggle around on these pins. It's also going to wiggle around. But as long as we can meet all of the tolerances, you have to be able to be up against this face, be able to on these holes, and as long as this thing, so this bracket, the holes could move a little bit. This hole could be up, this hole could be down. As long as it clears the pins and clears this, we can always take it back into the assembly and get it to adjust to put on within that. And if you take a look back at our drawing, I'll show you the part actually animated a little bit in the gauge. There it is, and you can see when it moves around on the gauge, right? That would be the MMC. You notice the bottom holes there? You see that would be maximum material condition. That's what the maximum material. You take a look at it, see it sitting on a gauge and see the holes as they got larger, they actually departed off a little bit, and that would be the maximum material condition. All right? So it gives you an idea what a gauge is, and maybe you see, we're getting right down to business. We're going after the most important things and telling you what's important here, what's important to us. Well, that ends our fuel cooler bracket. That was a pretty straightforward and a simple one. Maybe your first foray into tolerancing in 3D. I think you'll find that pretty interesting. I find that a lot of people like that tolerancing in 3D. In automotive, we do that a lot, tolerancing in 3D. I see it more and more. We have a standard, the Y1441, that talks about dimensioning or tolerancing parts and solids. You might take a look at that standard. It gives you some guidelines, gives you some understanding. Another way to look at it. And I think what it does is it tries to show you also that when you think about the parts, what you're doing is you're thinking about the tolerancing. Where the dimensions come and go doesn't really have anything to do. We don't even need the dimensions. Right there in the CAD file, we're looking at the tolerancing. All right, that's it for our fuel cooler bracket. We have another sheet metal bracket coming up, the battery box bracket. I think you'll like. It's a little more of a complex problem. It's going to be a little bit of a stack problem we have to do. So I'm going to turn it off right here and get ready, because we're going to do the battery box bracket next. So we'll see you then.